Okay, here we are on example number 4 from chapter 1-4. It says to sketch f of x is equal to x squared minus 1. Well, hey, we can kind of use our new skills about transformations, and you can think, well, I know what y is equal to x squared looks like. It would be if you have 0, 0, 1, 1, 2, 4, kind of go off the off there, and then negative 2, comma 4. So that's what if I write it in green, y is equal to x squared looks like. So what happens when I do y is equal to x squared minus 1? Well, I can think of it as a k value of minus 1. It goes down 1. We get a vertical translation of down 1. So I'll just go down 1 for each of these. Erase my old ones. Erase my greens. Got to be careful here. Okay, and then here's my graph. Get something that kind of comes right like that and like that. Okay, so there is my y is equal to x squared minus 1 in really messy writing. The question is now, will the inverse be a function? And I can say, well, if you recall from earlier, that if this function does not pass the horizontal line test, then the inverse, which is going to look a lot different, won't pass the vertical line test. So I can say, no, it will not. No, because y is equal to x squared minus 1 does not pass a horizontal line test. And I have exceptionally messy writing today. I apologize for that. Now it says use the graph of y is equal to f of x to sketch the graph of the inverse of f of x. Okay, so you remember there's kind of two ways to think about inverse. Number one is its reflection over y is equal to x. That's one way to think of it. And of course the other way is to switch your x and your y. There's my switch sort of symbol there. I think let's go with the second one here, because this can be a hard one to sort of think about the reflection over y equals x. It gets kind of messy. So just to prepare for it, what I'm going to do is I'll think about what my spots are. This is 2, 3. Right. This one here is 1, 0. This one is 0, negative 1. This one is negative 1, 0. This one is negative 2, 3. Okay, so I'm going to do, I'll use green here for my inverse function. So starting over here, instead of 3, 2, I will be getting, or instead of 2, 3, I'll be getting 3, 2. So that spot's going to go over here. All right. So again, just thinking about this reflection business here. So here's my y is equal to x. Okay, and you can see how this point reflected over there. Okay, my next spot was a 1, 0, so now it's going to be 0, 1. Okay, so now this one reflected over there, so you'll see this line is going to it'll look like that. So it's kind of a weird kind of reflection across that spot. 0, negative 1 now will be negative 1, 0. So this is an odd one. This spot reflects and lands over here. Okay, so we're going to have this little switcheroo going on. So I'm just going to graph this first part, the part where x is greater than 0. So just this section here is going to end up looking like this. Okay, so you'll notice that this is the part where x is greater than 0, and now this is the part where y is greater than equal to 0, because my x and my y values are switching. Okay, so now moving on, this blue dot here, negative 1, 0, reflects and gives a green dot there. My negative 2 comma positive 3 is going to give me an x value of positive 3 and a y value of minus 2. So that one reflects all the way over here. And so the second part looks like this. Okay, so if blue is my original, here's my inverse. So f minus of x, right? That's my inverse of f of x. Explain how we can restrict the domain of the original graph so that the inverse is a function. So right now it's not a function because it does not pass the vertical line test. So how could we restrict the domain so the domain is all the x values? Well, I'm going to pop over to my favorite software here for graphing. This is called Desmos.com, and here I'll just go back here. I'll just write it out here. Desmos, if we haven't done this as a class yet, .com, and it's really nice for typing stuff in and seeing how it works. So here I've typed in f of x is equal to x squared minus 1. And here is how, in Desmos at least, really what I do is I switch the x and the y, right? Instead of saying y is equal to f of x, I wrote x is equal to f of y. So this is what the inverse function looks like, the orange one. So this is what I just did. But what I'm going to do is I'm going to restrict the domain here. So let me recall, I need to restrict the domain in this software. I need to use these little curly braces, and I'm going to say x is. Now what I want to do is restrict it and just say that it is greater than 0, and then we'll see what happens here. Is greater than 0, and check that out. So now instead of having my full function, I restricted the domain, so x is greater than 0, and now look what happens to my my inverse. Is that a function now? Yes, it is a function. Okay, I've said that now this passes the horizontal line test. The original function passes the horizontal line test, so that the inverse now passes the vertical line test. So going back to our notes here, explain how we can restrict the domain of the original graph so that the inverse is a function. We can say that x is greater than or equal to 0. So what we end up getting as a graph then, what was my original one, was blue. Let's go back to blue. So we get our blue, and it just goes along like this. That would be my original function. And now what I get as a result for my inverse function is, and I think it goes kind of like that, right? That's what I get as my inverse function. So you'll notice that in y is equal to x squared minus 1, the vertex of my original function was right there. The vertex was at 0, was at 0 comma negative 1. Whatever this x value is, whatever that vertex is, if when you need to restrict the domain, make it either greater than that or less than that, right? And we can include the 0, so you can say greater than or equal to 0. So that's the point. You can either say x is greater than 0, and you can include that if you want, or, and this is coming up, oh, and I forgot to erase my earlier work here, so I'll do some erasing here. We'll catch up in a second. Is it possible to give another answer? And the answer is yes, you can make it less than or equal to 0. So there's the other option. So I'll just put that, or you can say x is less than or equal to 0. So what would that look like if x was less than or equal to 0? You know what, maybe I'll just draw a quick little sketch of it. In blue, it would be this one, right? And what would that look like for my green one? My green one would be kind of like this, and it would end up looking like that. Let's go take a look at Desmos, and it'll do a better job of showing it. So I'm going to change this restriction here, and instead of saying is greater than, I'll say is less than, and there we get it. So it's kind of funny looking, but yeah. So here is my original function, and there's my inverse of the function. I've said now that x has to be less than or equal to 0, and now in my inverse function, y is less than or equal to 0. All right. Write the equation of the inverse function. Okay, so we'll get a little bit of space for this one. So we'll start off and we'll say that y, alright, what was it again? F of x was equal to x squared minus 1. So my first step is to change that f of x to a y. Y is equal to x squared minus 1. And now we're going to switch the x and the y, and that's when it actually becomes the inverse. So I'm going to say x is equal to y squared minus 1. But now we're going to have to solve for y. So to get y by itself, I'll add 1 to both sides. So I'll say x plus 1 is equal to y squared. Running a little bit out of room, so I'll just go up to the top and I'll rewrite it. I'll say y squared is equal to x plus 1. And now when I do the square root of both sides, because I'm taking something, I'm squaring it and then square rooting. Like if I take, 2 and then I square root it, I squared and then square root it, I get back to 2. But if I started with negative 2 and then I squared it and square rooted, I would also get a 2. So this kind of shows you that you don't know exactly whether this was a positive or a negative here. So at this point, when I do the square root of both sides, I'm going to say that y could have been positive or it could have been negative, the square root of x plus 1. All right, and so that shows us that really we could write this out: y is equal to the square root of x plus 1, or y is equal to the negative square root of x plus 1. It shows us that it's not really a function, because for any one y value, you've got two x values that are going to be associated with it. Okay, so it's if you look over here at our original, if I draw this out here, we're going to have two, actually I said that the wrong way, didn't I? For any x value, I've got two different y values. So here, if x is equal to 1, y could be a positive or y could be a negative. So if I, looking over here, if I put in any value for x, if I put in a 1 here, I could get 1 plus 1, and I could get the positive square root of 2, or I could get the negative square root of 2. So 1x has more than one y value attached to it. And so that's why, if you noticed, it said write the equation of the inverse relation. It didn't say of the inverse function, it said of the inverse relation. So this is why we get, and in fact, that's a good enough way to write it. That's why we get that shape that we do. Okay. Next section is proving, I'll do some more erasing here, proving that, I'll leave this, proving that functions are inverses of each other. So it's difficult to prove that two functions are inverses of each other graphically, but what we're going to do is we're going to prove that the functions are inverses of each other. We're going to show this algebraically. So we're going to use that as some algebra coming up. So if f of x is the inverse of g of x, then, oh well, now isn't this an interesting thing here? We get, this is how you would say it. You say f of g of x is equal to x. Okay, so what does that really mean? Well, I talked earlier about a way to think about functions as sort of like input-output machines. So here we're starting with an x value. Here's the x value. We're plugging it into g. And then what comes out of that, we're plugging into f. And then if what comes out at the very end is x, then we know it's an inverse. Okay, so if f of g of x is equal to x, if when we plug it in and it's gone through both of them and x comes out again, then we know that they're inverse. Whatever g did, f undid it. And that's what the inverse is. That's the idea of it. So essentially what we're doing is we're substituting x into g of x, right there. We then substitute this result into f of x. If we end up right back where we started, then we'll show that these two functions are inverses. Okay, oh, I got to do some erasing here. I'll just pause. Okay, so in this example, we're going to show that f of x is equal to 3x minus 5, and g of x is equal to x plus 5 over 3 are inverses of each other. And we had just said that what we need to do is show that f of, and I'm going to just change colors here, g of x, I know this is a lot of colors here. So we want to find out and prove that that is equal to to x. Okay, so if this is equal to x, try this again here. If that is equal to x, then they are inverses. All right, so we're going to start off and we're going to plug x into g of x, and what comes out? Well, how does this work again? We'll say, I'm going to write out a lots this first time, and then you don't normally have to put that much in. So we say we're going to take x and we're going to put it into this g function. What comes out? What comes out when we plug x into g? Well, that's how this is defined for us. If we put an x into it, what comes out is x plus 5 over 3. So what I'm going to do is I'll say, okay, instead of saying this if statement, I'll just say, okay, I'm going to find out what is this equal to. All right, in the next line, I'll say, well, if I plug an x into g of x, what comes out is x plus 5 over 3. Okay, let me just talk about like how that part worked. So if I say that g of x is equal to, I should do some x plus 5 over 3. Really, whatever goes inside of here comes out here again. So I could say, well, what if I put in, I don't know, let's get crazy. What if I put in like a star here? What comes out is a star plus 5 over 3. So it doesn't matter what goes in here, that's what comes out. Okay, same thing now for f. So f is f of whatever we put in. So we'll start off by putting in x, and we'll replace that, is equal to 3x minus 5 over 3. So what happens if we put in something really crazy? You know, again, what happens if we put in, I don't know, a something like that? Now, again, this means multiplying here, so I'll put a parenthesis, and then this is a plus, right? Whatever we put in here, we'll say 3 times that plus 5 all over 3. So looking over here, well, we have something to put in. We're plugging in an x plus 5 over 3. So what we're going to get is, and I'll just make some room, what we're going to get is 3, I'll do it over here, 3 times, this is our x plus 5 over 3, minus 5. So here was our definition of our function. So instead of plugging in an x, we're plugging in an x plus 5 over 3. And so our result is equal to, well, what happens when this gets multiplied by 3? This 3, if you can think of 3 over 1 multiplied by x plus 5 over 3 minus 5, for those of you that like to think about fractions that way, we can say, oh, that 3 cancels out with that 3. So really we get x plus 5 minus 5. So we get x. So then therefore we've done it, haven't we? We've shown that f of g of x is equal to x. So therefore they are inverses. Okay, so I spent a lot of time on that first one. There are 2 practices here. You know what, I'll go through the first practice and then I'll let you do the second practice. I'll show you that it really doesn't have to take that long. So really what we're going to say is, what is f of g of x? I'm going to say, okay, g of x is the same thing as this x plus 4. So I'll say f of x plus 4 is equal to, now I go back here and I say, well, if I'm putting an x minus 4 in here, if this was x plus 4 in there, then here I'm going to put in an x plus 4. So this is equal to x plus 4 minus 4. and that is going to be equal to x. So therefore, inverse. Okay, I'll pause for a little while. I would like you to try this next practice, try B, and then I'll show you the answer. So you pause, give it a shot, and I'll be right back. Alright, so we start off and I write f of g of x, and we're going to find out what that is. If it's equal to x, we know that there are inverses, and so the first thing we can say is I'm going to plug in my g of x. If I plug in an x, what comes out is x minus 3 over 8. So my next line is f of x minus 3 all over 8, which is going to be equal to, now here if I look at f of x, wherever I see an x, I go 8 times that x plus 3, so it's going to be 8 times my input of x minus 3 all over 8 plus 3. So that's going to be, my 8's are going to cancel it out. I'll get x minus 3 plus 3, so I'll get x. So therefore, inverse. They are inverses. Okay, one more time. I'll just pause for a little while. I want you to try part C, and then I'll show you the answer. All right, maybe I'll try this one in blue. So I'll say that f of g of x, I'm going to find out whether or not that is equal to x. G of x is equal to 2x plus 2, so I'm going to say f of 2x plus 2 equals. Now wherever I see an x in my f function, that x shows up here again. So if I'm plugging in a 2x plus 2, where I see this x, I'm going to write a 2x plus 2 minus 2 all over 2. So what happens in my numerator? I have 2x plus 2 minus 2, so that's going to be equal to 2x over 2. So that's going to be equal to x. So therefore, yes, inverses. Okay, so we've done it, and I think that's the end. Okay, and so we are all done for now. Thank you very much.